let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another installation of Math 212, Calculus 2. We have some exciting stuff planned for today. At least I'm excited. Can't wait to get to it. Before that, though, of course, we have to finish up some problems that I left for you guys to do last time. So we're just going to kind of rush through those. Hopefully you guys tried it. So you're not, you actually tried it. You're not just following me. Let's actually figure this out. Let me share my screen here. So yeah, this is what we had to try for last time. Again, we looked over conic sections last time. Conic sections are, at least the versions that we care about, are guys like circles, ellipses, parabolas, and hyperbolas. There are other ones, but we call them degenerate, but we do need to know how to graph these. Students usually remember how to graph parabolas and circles, so I didn't really talk about those at all, but ellipses and hyperbolas, very important that we know how to graph those. And so we talked about how to graph those by creating that box. You create the same box for ellipses and hyperbolas. However, you deal with that box differently. Degenerates. Yeah, okay, so so we had a couple examples, and I even left the answers here for you to actually check your work at the end. But that being said, not actually much to do here, so I'm just gonna do them. Let's actually get this show on the road. Right. So we have this guy here, identify the conic, state its center, and sketch. This one is in a pretty nice form so far, but we can get it nicer. How can we get that to be nicer? What would you think to do to get into some standard form? Right, you divide both sides by 21 because all the standard forms that look like this would have 1 on the right side. The only one where you don't really would have 1 on the right side with something that looks similar to this would be a circle. However, for the circle, both coefficients of the square terms have to be the same. If they're not the same, then of course it's not a circle. It's either a hyperbola or an ellipse. To figure out how to actually graph it, you would just make sure that the right side is 1. So we divide both sides by 21. This would give us x minus 2 squared over 3 plus y minus 2 squared over 7 equals 1, which of course we would think about this guy as the square root of 3 squared, and we'd think about this guy as the square root of 7 squared. And so that we can identify this as an ellipse because it has a plus sign. Both of the square terms are positive. And so this gives us an ellipse with center 2, 2. And so we can actually start to graph that. Okay, so all right, where are we? So radical 7, that's a little bit bigger than 2, a little bit smaller than 3. So that's somewhere between 2 and 3. So let's say I have 2 here, 2 here. That's going to be my center. I would move left and right by A. A is radical 3, which is a little less than 2, so it doesn't quite hit the y-axis, but it gets somewhat close, and it goes to the left and the right. So we move to the left and right by square root of 3. Square root of 3 is that distance there. That's because that's under the x. What is this guy? Then we move up and down by the guy that's under the y. So in this case, it's going to be radical 7, which is a little bit bigger than 2. So we're going to pass that. Go up here. And that allows us to create this box. I think I switched to green and the blue last time, but it doesn't matter. So this is like the skeleton for our ellipse. And then we just mark all these corners. These are the vertices of the ellipse. The major vertices are just the one along the longest axis. So it's along the blue axis here. We have the major axis. And that's our sketch right there. Okay, and that was, that's problem 2. Now we can move on to problem 3. This one, slightly a little more complicated because everything's in an expanded form. So I first have to get everything to look correct. By the way, you guys can actually type out the standard form of whatever conic you think it is. Let me know that you actually got to the answer before me or something. So, right, so here we group the y's, group the x's, I can move the 31 to the other side. Factor out of 4. And that's kind of how it is. So remember how to complete the square. We're going to add half the coefficient of the linear term, square it, subtract that.
Can't you add it to the other side as well?
Yes, but I find that students make a mistake there because they tend to forget that they have to multiply by this coefficient. So technically, if you wanted to add the 3 squared to the other side, you'd have to remember to multiply by 4 in addition to doing that. So as long as you remember that, we're good. I like to add them add and subtract inside the parentheses so that when I multiply out, you literally can't forget the fact that you had to multiply by the coefficient. So that's why I do it this way. So the first 3 terms would be the complete square, y minus 3 all squared minus 9, x plus 1 all squared minus 1. So this is going to be 4y minus 3 squared minus, what's 9 times 4?
36.
So then I have this. And here, the minus 36 plus 1 is minus 35. Bring it over there, it becomes positive 35, so it only becomes 4. And of course, I would divide both sides by 4 to get it in standard form. And 4 over here. All right, so what is this object and what is its the center? All right, it's a hyperbola. I know because one of the square terms are negative. The center, minus 1 comma 3. Okay, so I didn't fool you there with rearranging the, isn't what a quarter? You said, isn't it 1 over 4? Where should be a 1 over 4? No, couldn't put one past Nat again. Got to wake up pretty early in the morning to fool her. Anyway, so we have a hyperbola with that center. And so now we can graph it -1, 3. So let's do -1, 3. Oops. Now, under the x, there's a 4, which you think of as 2 squared, which means you move 2 units in the x direction either side of the center. So that is going to be, it's going to go all the way over here and go all the way over here. So this actually would show up around 1 on this side, and it will show up here around 3 on that side. Then under the y, there's like a 1 squared. So I'd move 1 unit up and 1 unit down. So move that 1 unit up. So that's around at 4. Move 1 unit down. So that's around 2. Then I create this box. What do we do with the box now, since we're doing a hyperbola? Diagonals. You have to put in the diagonals of the box. Right. So now I have if you made the sound effects, it increases your drawing power. All right, so now let me know, is this a north-south opening or east-west opening? Right. Yeah, Natalie knows what I'm talking about. The sound effects do help, right? When you go that like without, if you don't do it, like it's not as good. Yeah, so this is going to open up and down. So your vertices are on the vertical axis, because the y is positive, is going to open in the y direction. So that really should be asymptotic to that. I don't know. Chat box was in the way and I didn't want to move it. I got lazy and now it's like, it's not quite right. Okay. Actually, you know what? I didn't make the sound effects either, so that made it even worse. So now I'm doing the sound. It's a little better. Yeah, see, you guys saw a proof right there that it didn't work because I was like talking while doing it instead of doing the sound effects. So that's our hyperbola. All right, so now we hopefully know how to draw ellipses and hyperbola, and those were 2 more examples. So that's it for conic sections. We didn't really cover this section in detail. We didn't need to, didn't want to. However, we're going to get to a point where we're going to be sketching surfaces in 3 dimensions, and it's going to be very important to know how to sketch things like parabola, circles, ellipses, hyperbolas, all that good stuff. You should know how to sketch everything: straight lines, circles, parabolas, ellipses, the usual suspects. Make sure you know how to do those. Ellipses and parabolas, students often forget that though. So now let's move on to the next phase. Dum, 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 dum. All right, so this is what it's about, the moment we've all been waiting for. At least I've been waiting for. So we are going to learn some 3D stuff. We're going to talk about 3D space. Finally, calculus is going to start getting interesting. Living our lives in 2 dimensions wasn't exciting enough. We are now going to learn about 3 dimensions. And again, we're going to take it really slow. We're going to start from scratch. We're going to build up this universe, how things are going to work. So I'm going to talk about 3D space, talk about equations in 3D, what they kind of mean. We're going to sketch a few naive surfaces. Later on, we're going to learn to sketch some more complicated surfaces. I'm also going to talk about vectors and introduce operations on vectors, because when you're in more than 2 dimensions, vectors is really the way to get things done. You want to find locations, you want to sketch out curves, you want to sketch out surfaces and solids. Conceptualizing it as being a vector or having vectors trace things out for you is the better way to do it. And we are going to talk about, see, you see when you start that sentence with ugh, I don't know if you're being sarcastic. So at one point you're like, I love vectors. And then on the others, oh, maybe you should have like an ack or gasp. I don't know. I don't know if people use ugh when they actually like something. Okay, all right. So that's where we're going to go. Vectors is not going to be this section though. We're going to start chapter 12, section 12.1, the 3-dimensional coordinate system. Now, your book actually at this point actually talks about 1 coordinate system. It's actually the rectangular coordinate system, even though it doesn't title the chapter like that. It only mentions the rectangular coordinate system. Turns out in Calc 3, by the end of Calc 3, there are going to be 3 main coordinate systems you're going to know about, learn how to think in, learn how to draw in. These guys are the rectangular coordinate system, the cylindrical coordinate system, and the spherical coordinate system. These guys are very useful for very different reasons. But right now we're going to do the basics. Just like how we learned about the rectangular coordinate system for 2D, there is an analogous system to locate things in 3 dimensions. So let's actually go to that. So remember, we locate things in the rectangular coordinate system in a 2D or coordinate system. You have your axes. Here's your X, here's your Y. If I wanted to find the point, for example, 2, 3, I find a 2 on the X, I find a 3 on the Y, and I kind of emanate lines from them parallel to the other axes, and boom, where those lines meet, that is location 2, 3. Right? So that's the rectangular coordinate system. What we're going to do now is we're actually going to add a 3rd axis, right? And we're going to do things in 3D. So here's how it would look. Let me move this out of the way. Here's how it would look, how you would draw a 3rd axis. We draw it like so, boom, boom, and boom. You put your X right here, you put your Y right here, and you put your Z right here. And of course, there are negative portions to this. The negative X-axis would run along this direction, negative Y would run along that direction, negative Z would run along that direction. Now, your entire lives, what you've been doing is before now, we've all had a bird's eye view. We were looking down like that. These little eyelashes. Before we've had a bird's eye view. Looking down. Now that phrase bird's eye view is not accurate in the sense of what it usually means. Because when someone says you have a bird's eye view, they think you're overlooking everything, you're seeing everything, nothing can get past you. We are going to learn that a lot of things got past us in 2D, and we're going to learn that we've only been seeing up to this point in our lives a shadow of things to come. What we were seeing in the 2-dimensional world wasn't reality. There was more to it, right? We were like in the matrix and we didn't really understand how the world was working. We're going to start to learn how the world works now. So bird's eye view, looking down at the XY plane. Right, so that's where we were. But now that's how we are going to imagine it. So how would we locate a point? Let's say I wanted to locate a point like 2, 3. Let's say I wanted to locate a point like 1, 2, 3, right? And I wanted to find that point. What I would do is pretty similar to before. I would just draw my axes. And again, I would find 1 on the x, just as we always did. I would find 2 on the y, just as we always did. I would then emanate lines from the x and the y. And then now what we also do is we also find a third number on the z coordinate. And we actually lift ourselves up vertically until we're on the level of that. And that is our new coordinate. Now it's hard to actually visualize that this is in 3-dimensional space, but now you see that it's in 3-dimensional space. What can I tell you? Now the rectangle before is now actually like a box. You can actually imagine that. You can imagine that there's a box here. Right? So now our rectangle comes like a box. Yeah, you see it, right? Okay. So this is one of the effects of 3 dimensions. We now think of our coordinate as being at the corner of a box that is opposite the origin, right? Similar to how before we were just looking at our point as being on the corner of a rectangle opposite the origin. Now it's at the corner of a box that is opposite the origin. Okay, all right. It's already more interesting than 2D, right? Maybe I should leave that guy here. All right, so just learning like, ooh, right. Yes, that's why it's rectangular. All right, so now let's actually start talking about how we're going to name things and all that sort of stuff. And by the way, this is how we will sketch the 3D axis, right? So meaning in your book, whenever your book talks about positional language, like, oh, you're to the right of the XY plane, or to the left of this, or you're above this, it's assuming that you have the orientation that I drew here. There are other ways to sketch these axes together. I mean, sometimes people use others.
Not mix it up, right?
Sometimes people use like a Y here and the X there, just like they would have drawn on paper, and then they put the Z down here. But we are never going to look at it that way, right? So not for us.
Professor, are you allowed to mix X, Y, and Z up, or is just it always have to be like that?
Well, it has to be like this for us. That's what I'm trying to say. If you start drawing your X, Y, and Z any which way, then you're going to run into problems when you try to translate things as far as problems go, or if you try to sketch something or something like that. Like I said, there are going to be problems that are going to talk about positional awareness. They're going to say, oh, you're to the right of this object here, or to the left of this object. Well, if you change your coordinates for X, Y, and Z, what they say is to your right might be to your left, depending on where you wrote it, or it might be above you or below you, right? The only way to guarantee that you're going to coincide with all the things that we will be saying is to actually draw it in this orientation. So everything I will be saying, all the problems you'll be reading, all of that stuff assumes that you're sketching it with this orientation. That being said, let's actually get our bearings here, because we're in 3 dimensions and drawing it on 2-dimensional paper can be difficult to understand and visualize. So here, actually using the room that you're in can help you visualize this a lot better, right? So let's say you're the little man, you're in the room, or the little woman, and you're facing the corner. Then what you can do is you can imagine that the x-axis is running along the bottom of where the wall meets the floor, running along the edges on your left. Your y-axis is running along the edges on the y, and your z-axis is running up straight in the corner. And the right wall is what we call the YZ plane. The left wall is going to be the XZ plane, and the floor you're standing on is the XY plane, right? So you can look in a room to kind of get your bearings. On your left is going to be the X, on your right is going to be the Y, and running straight up in the corner of the wall is going to be your Z axis. That's how you want to measure. Imagine it. Now, of course, this is not the full three-dimensional space. This is just a part of the three-dimensional space. This here, where you're standing in, it's called the first octant, right? Because you'll realize that if you split the space with these three planes, the YZ plane, the XZ plane, and the XY plane, you'll actually split space into 8 compartments. So it's not like back in 2D where there were only 4 compartments, there were 4 quadrants. In three-dimensional space, you now have 8 octants. So if you want to imagine the first octant, that's like the room you're standing in. If you want to imagine like the entire three-dimensional space, it's more beneficial for you to imagine it as if you were standing in a two-story building, right? So you actually split things into 8 compartments. And so you can imagine that you're in a 2-story building where you are somewhere standing on the 2nd floor, right? So in your room, you are in the first octant. When the X is running along your left, the X is running along your left, the Y is running along your right, and the Z is running positive. Of course, down, running along that corner into the room below you is the negative X axis, and then that's the negative Z axis, the negative X axis, negative Y axis. If you look to the room behind the right wall, that is called the second octant. If you look to the room behind the wall to the left of that room, that's the third octant. Look to the room in front of that, that's the fourth octant. The fifth octant would be the room directly below you. The sixth octant would be the room that's to the right of the room directly below you. So look to the room to the right, behind the wall, underneath that floor is going to be the sixth octant. Seventh octant is all the way below the third octant, and the eighth octant is below the fourth octant. Okay, so you measure the octants around the top floor the same way you'd measure the 4 quadrants. Think of going around this counterclockwise and measuring it. Then you start in the room below you, that's the 5th octant, and then you number them again counterclockwise. Just so you know, pretty much the only octant that will be mentioned by name is going to be the first octant. That's the one where you really need to know. I've never seen a problem that asks you to talk about, imagine when you're in the 5th octant. I've never seen something like that. Imagine you're in the 7th octant. There is no 7th quadrant. There's a 7th octant. Quadrant means 4, right? So be careful. You don't call it a quadrant anymore. You call them octants now. Okay. So there are 8 octants. And I'm speaking a little bit fast, but everything I'm saying here I actually typed out in words at some point. So quadrant is 4. So in 2D, there are 4 quadrants. In 3D, there are 8 octants because there are 8 compartments in 3-dimensional space, and there are only 4 compartments in 2-dimensional space. All right. Now let's talk about objects in 3-dimensional space, right? So we're going to look at some simple planes, we should call them. The simplest planes that you would have is like something like a variable equals a constant, like x equals a number, y equals a number, z equals a number, right? These are the simplest planes you'll see. Now in 2D, what is, so let's say we're in 2D. What does x equals 1 look like? What is x equals 1? If I told you we're in 2D and I say x equals 1, what am I talking about? What would you say I'm talking about? What object am I describing? Right, just a vertical line passing through x equals 1, right? So that here, okay, so that here, that's the line x equals 1, right? Vertical line. In 3 dimensions, when I say x equals 1, what am I talking about? Is it just a line as well?
It's a plane parallel to the y-axis at x equals 1.
Exactly. So now, if you go in 3 dimensions and you look at the axes, let's say I'm drawing the axes right here. So here's X, here's Y, here's Z. Here's where X equals 1, right? Now, of course.
Would the plane be ZY actually?
Right, it's parallel to the YZ plane.
Yeah.
Now, this is the line that we've always, now the line that we know is X equals 1 is this, but it turns out X equals 1 was never really a line. X equals 1 was actually a plane. It just appears to be a line in 2 dimensions. It looks like a line, but what we were really seeing was a plane slicing through the XY plane. We saw the shadow of what a plane was. You will notice therefore, because if I move directly above that point, my X is still 1. If I move directly below that point, my X is still 1, right? So whether I can go directly above that point, my X will be still 1. If I'm below that point, my X will be still 1. If I move to the right and just stay on that line, my X coordinate is 1 at all these places. So you'll notice that there's a whole sheet. There's an object that's like a whole sheet that's running, and it's expanding in all directions. So this keeps extending up forever, keeps extending to the right forever, keeps extending to the left forever, keeps extending down forever. And that is what X equals 1 actually is. X equals 1 is a plane, right? Now it's parallel to the YZ plane, okay? Now, if you move over a little bit and we look at Y equals -2, the same sort of idea would hold. If I look at Y equals -2, basically what's going on is, and I can move this out a little bit more. So if I look at Y equals -2, essentially what is that guy? Well, if I draw my 3D axes, where is this guy going to be located? Describe where this guy is showing up. Try to describe in words where the plane Y equals -2 would be.
According to what I'm assuming, probably it would be around -2, like, on the negative Y part. So you would plot your point on negative Y equals -2. It would be just be a horizontal line,
In the XY plane, yeah.
Yeah, and therefore you would just put these 2 arrows on the, on the front and in the back.
Right. And it looks like that. Right? So this guy here is actually parallel to which plane? Which reference plane? So the reference planes that we're talking about up here, again, I said this in the notes, but I didn't verbally say it. When we refer to the XY plane, the YZ plane, or the XZ plane, we refer to those as the coordinate planes.
The example
right?
that we did just now
planes.
was the XZ plane. It's the XZ plane.
Right, so this is parallel to the XZ plane. This one over here was parallel to the YZ plane. Right? This one is behind the XZ plane. You can see that reference being used, but it's actually parallel to the XZ plane. So it's standing straight up. It's a wall that's straight up. It's pretty much a wall that is parallel to this purple wall that we see here, but you can imagine that it's like the back wall of this room right here that we're seeing. Right? If I look at, say, Z equals 3, again, I would just find where Z equals 3, and then it's just going to be like a flat plane hovering in space, it's actually parallel to the XY plane. But it's hovering above. Like if you were standing in this room, this would be just something hovering above you at like 3 feet off the floor. If you're very short, I suppose. Yeah, so these are some objects. What about y equals x? What would that look like? So you would first go, you draw in your axes. You remember how y equals x always looks. It's just was some guy that's kind of coming out here. So it's going to be very hard to see, but it's running along. Maybe I can give a little different perspective. Slant it a little more. So just think of this thing coming out. That, and this line that this is slicing through, that is the line y equals x.
Professor, what happens when you don't draw this, 3D shape, instead you just draw the line?
Then you'd be wrong.
Would be wrong?
Yes. So if you have this, it's only a line in 2D, right? Because all you are seeing, this blue line here, was actually the guy that's on the floor right here. But there's more to x equals 1 than that, right? You were just seeing a shadow of x equals 1. That's not really what x equals 1 is. X equals 1 is a plane. So if I ask you to draw x equals 1 and we're not in 2D and you draw a line, you're wrong because you're drawing a line. And a line is very different from a plane. A plane is a 2-dimensional object. A line is a 1-dimensional object. So it's not the same thing. So question, what would the object x squared plus y squared equals 1 look like? What is that? X squared plus y squared equals 1. What is that?
Wouldn't that be a cylinder at center 0 with radius 1?
Right. So just like yesterday, we looked at x squared plus y squared equals 1, and I was like, yo, that's a circle, right? That's center at the origin, radius 1. It is no longer a circle. Again, a circle was only a part of the truth. It's only a circle when it slices through your xy plane. So now we know the real truth. X squared plus y squared equals 1 is not a circle. X squared plus y squared equals 1 is a cylinder. It looks like a circle when you were looking down in the xy plane. We would look down and we'd see a shadow of a circle, right? But it's not really a circle. There was so much more to the picture because you see, if you go up a level, and x squared plus y squared equals 1, you'll see another circle. And if you go down a level, you would see another circle. So it's a bunch of circles running up and down along the z-axis. So it's actually running like that, running like that. And of course, this is going on in forever in both directions. And it's actually a cylinder. So this here is a cylinder. Now we're going to learn about sketching cylinders more generally. A lot of people who, when they hear the word cylinder, they always think circular cylinder, which is what I just drew, but it's not always a circular cylinder. We'll talk about cylinders more generally in the mathematical sense. But yeah, x squared plus y squared equals 1, not a circle. It's actually a cylinder. It's a circle to the people still stuck in the 2D matrix. But we are taking the red pill today. So yeah. Now, let's look at some other things. Distances in 3-dimensional space. How do you actually measure distances? It turns out that we actually measure distance in 3D space in pretty much the same way that we measured it in 2D space. So that's not much difference. We just extend the formula a bit. We just add a variable to the formula. So we have a distance formula in 3D, and it just looks like the distance formula in 2D, but we add the third variable. So if I want the distance between x1, y1, z1, and x2, y2, z2, then it's the square root of x2 minus x1 squared plus y2 minus y1 squared, plus now we add the third variable. And this is because Pythagoras' theorem still works in 3 dimensions. So this is like if I had a point here and a point here, and I care about this distance here, what I have is, one, there's a shadow of those 2 points in the xy plane. And then I can find their distance by, it's just d1 by the square root of, I don't want to have to write it down on this thing. The 2D distance formula. Or more specifically, what we can do is in the xy plane, we can create a triangle. And so here, this will be y2 minus y1 squared. And over here, I would have x2 minus x1 squared. And if I add these two, I would get this blue line here equals length of the blue line. Length, the blue line, squared. And so I can translate that distance up here, and then I use that guy to sum up here with this new one here, which is now the z2 minus z1 squared. And then down here, I would have the x2 minus x1 squared plus the y2 minus y1 squared. And Pythagoras' theorem gives me that this guy is going to be the sum of the three. All right, so we can apply Pythagoras' theorem in 3 dimensions and get a 3-dimensional distance formula. Now we want to look at something like a sphere. A sphere is just a point that is equidistant from a reference point. So if h, k, l is the center, the distance between that and a point on the surface is always the same. We call it r. And so we can set r to be the distance formula here. So we can set r is equal to the distance between x and h squared plus y and k squared plus z and l squared. And then if you square both sides, you get the equation of a sphere, which is this guy. Right. By the way, if you're interested in what a 4D dimensional sphere would behave like, you can actually check out this link. It's pretty cool. Fun fact, if you were a 4-dimensional being, you would have a lot more choices for hairstyles, because it turns out in 3 dimensions, if you had a sphere covered with hair and you tried to comb the hair so that it's flat on all edges of the sphere, it's actually impossible to do this without creating a part or some sort of cowlick kind of bang thing going on. You can't actually comb your, so if you have a perfectly round head, you couldn't actually comb your hair to be flat on your head without creating a crease or a part or a cowlick or something like that. And you don't believe me, you can try it. It's impossible to do that in 3D. In 4D, it's actually possible on a 4-dimensional sphere. So if a sphere was covered with hair in 3D, you couldn't comb it all flat without some sort of disturbance. In 4D, though, you can. 4-dimensional spheres are crazy, and it just gets crazier the higher you go up in dimension. Now, just like how with the previous section, we are often going to need to be able to rewrite equations to be in standard forms where we can understand what object we're looking at. Now, here's an equation. Basically, I want you to show that this is the equation of a sphere. What is the center and radius? Nothing new here, nothing to see here, folks. It's pretty much we're going to complete the square, but we do it with 3 variables at a time. So we would bring everything to one side and group all the variables together. So I can subtract 4x from both sides, add 2y to both sides, and then add a z squared to both sides. Then I would complete the square. I would add half that coefficient, square it, add half that coefficient, square it. So on this side, I have to add those guys. This would be x minus 2 all squared, plus y plus 1 all squared, plus z, technically it's z minus 0 all squared. And on this side, I would have 5. And so this now looks like a sphere. Center is 2 minus 1, 0. Radius is radical 5. So nothing new there. This is going to be something that we're going to need to be able to do a lot of later on. We're going to need to be able to rewrite things and understand what object we're looking at. So in 3 dimensions with these 3 variables, you would know that this is the equation of a sphere. A sphere is a 2-dimensional object. It's actually assumed to be hollow. So this is a 2D object. A sphere is hollow. Just the skin. If I wanted to say that it was solid or filled, I would call it a ball, not a sphere. A sphere is a 2D object, so just so you know, it's a technical term. You don't just call anything round a sphere. You can call things spherical, even if they're filled, but you can't call it a sphere, strictly speaking. All right. Another thing we're going to want to know how to do is regions in 3 space. Going to be very important. Not only is it important in this class, but it's going to be uber important in the next class. In Calc 3, are you kidding? Woo. We need to know how to talk about regions. And again, we're just going to be just jumping in and just kind of getting wet and exploring things. So here, let's lead our way into it with R2 example. So let's say I wanted to sketch y less than or equal to x in R2. What would that look like? So we're in 2-dimensional space here again, just for comparison purposes. Of course, y equals x would be the line going like that. And I want the y to be less than or equal to x. So I want the set of all y coordinates that are always less than or equal to the x coordinate. So if you look up here, for example, you would see that this is the point 0, 1. So does not work. However, if I look over here, I would have 1, 0. And that does work. So I know the region I care about is this region over here. Right? So that's how you'd figure out a region in 2D. Now, of course, another thing that you would remember from 2D, sometimes you can have a strict inequality. Does anyone know how we show a strict inequality? Dashed lines, exactly. So when you draw a dashed line, that says the boundary is not included. But you can still shade the region. It'll be everything on this side of the line. So for this, boundary not included. So that's our drawing a region in 2D. Now, things are much more exciting drawing regions in 3 dimensions. So let's actually do that. So this is something that we want to draw in 3 dimensions. Okay, so we're in 3 space now. Dead giveaway is that there is a Z there. However, just because we're thinking of a curve in 3 space does not mean that all the variables will be visibly present. We'll get to that in a little bit later on. But for now, here's a region that I want to sketch. X squared plus y squared plus z squared is less than or equal to 1 into the first octant. What would that look like? Can you describe it? We're actually going to do this later. If I were to ask you to describe that region, what is that region?
That would be 1/8 of a sphere, right?
Right, that would be 1/8 of a sphere. Where would that part of the sphere be? In the, well, I just kind of tell you in the first octant, I guess.
Yeah,
So how would you actually do that? So you would look at this. Now, and here's a pro tip when you're sketching things in 3D, this is going to come in handy later. Even if you don't want the entire sphere, because clearly, as she just said, we want 1/8 of a sphere, it's very good to sketch the entire object that you want to begin with, and then you kind of slice off the pieces that you don't want. So what do I mean by that? What do I mean by start with the object that you want and slice off the pieces that you don't want? So I know I want 1/8 of a sphere. Let me just make things a little wider, because before the chat box was in the way. Don't know if I love that angle. So first you would actually draw the entire sphere. You draw the entire sphere, right? So how would you draw a sphere? Well, you draw a big circle. To kind of make sound effects like this. Then you draw an equator. Right, so that is that would look like a sphere. Now what you do is you just look at what parts you want from that sphere. You actually want to slice off here. That's the part where it intersects with the XZ plane. You slice here, the part that intersects with the YZ plane. And then you slice here, the part that intersects with that plane. And let's make this a little thicker, maybe. Right, and that's our sphere. So it's 1/8. Dress it up and sketch it up and shade it and right. So that is 1/8 of our sphere right there. Right. So it's like a dome or an orange, and you slice it in half, and then you slice that half in half, and then you slice that other half in half, and you would be left with that guy. You'd be left with like a part of that sphere. So it's just a little wedge portion that you have. So it's like a little. That's what you have. All right. So that's how you would sketch a sphere. And as you can see, you don't have to be like an amazing artist or anything. You just have to understand like how things relate to each other. Now, here's a question, a very interesting question. Could you describe that region? Now, this is kind of a foreshadowing here. Let's see who was paying attention last class. can you describe this region in terms of polar coordinate inequalities? So here is it in rectangular inequalities. And I mean, I would also need some other stuff, right? So in rectangular, I would say something like, I know that x squared plus y squared plus z squared should be less than or equal to 1. I also want my x to be greater than or equal to 0, my y to be greater than or equal to 0, my z to be greater than or equal to 0. That would create this region here. What about polar? So now polar is when I think in the xy plane, I think of the same r theta as we had before. So it's going to work the same way you think it works in that way. But there's also going to be a third axis added where we measure the z. What would you think of as the cylindrical? This is called the cylindrical. Well, it's a region, so you have to have like a inequality. R goes from 0 to 1.
Would theta go from 0 is less than or equal to theta is less than or equal to pi squared? I mean pi over 2?
Pi over 2, right?
And
in
then
fact,
C
if I
would
want
be
to
the same as
emphasize
R, right?
And if I wanted to emphasize the z part, I can say something like z is less than the positive square root of 1 minus x squared minus y squared. That might help you. So can you tell me a boundary for z in this system? So you can continue, whoever was talking.
Oh, I meant to say, wouldn't Z be the same as R?
No, because r is, what is it? The square root of x squared plus y squared, right?
Yeah, and then you drew
Your
out
z
the
is not that.
rectangular.
If you solve for z here, you don't get the square root of x squared plus y squared. In fact, you get the square root of 1 minus x squared plus y squared. But you do see that x squared plus y squared there, and so that's what you can use to your advantage. It's the square root of 1 minus r squared.
Oh.
Right? So you see that r is there, right? So it's different enough from this that would make it easier in a lot of contexts. Trust me, at this point, you're not going to appreciate it, but I just wanted you to get practice actually setting up a region in a different coordinate system. So this is a 3-dimensional coordinate system. I know because I had to tell you what's happening in 3 dimensions, 3 different variables. And that would describe this region, this part of the sphere. All right, what about this one? Now notice, if you were to describe this region, how would you describe it?
Would it be a sphere with radius equal to 2, but it's filled up until radius equals 1?
Uh-huh. And
If that
then
makes sense.
Right, so you just described this part.
Yes.
What do we do with these guys?
And then for y is less than or equal to 0, you would, and then z is greater than, so you would have, I want to say it's quadrant 3 and quadrant 4. I mean, no, octant 3 and octant 4.
Right, octant.
My bad.
Right. Yeah, I mean, it's hard. You're gonna have to switch. You lived your entire life one way, and now I'm telling you to do it another way. It'll take some getting used to, but yeah.
We'll get there.
Right, so you start off like that guy, and yeah, you notice that here there were actually 2 spheres in play. So there is a sphere of radius 2. There's another sphere inside of that one of radius 1. Now, of course, the negative axis goes along there, cuts that off. The negative y-axis goes along there, cuts that off. And then this goes along there, cuts that off. And then you are actually going to be filled out here. So where would that look like? Well, let's do this a little bit. I want to be the very best. You want to be the one that's from here back, right behind the XZ plane. Same thing for this one. So you have this part here. And then you want to be behind here. Right? So now, hopefully you guys are seeing this. This is kind of like, I don't know, like an avocado. After you slice up, you take 1/8 of an avocado and you took out the seed. Right? And now you have that 3D object. So it's like you have an avocado, you cut out the middle, you slice it in half, and then slice one of the halves in halves, and you have that little thing. So you have something that looks like a little igloo. Yeah, like an igloo as well, I guess, from those children's books. I never said it's avocado toast. It's just an avocado. Avocado toast. It's a ripoff. All right. So yeah, that's what we have for you today. So that's just it. The 12.1 starts out very simple. It's just introducing you to the 3D world, the 3D delicious ripoff. Yeah. Yeah, ripoff I can make at home. I'm not gonna go out and pay $15 for an avocado toast. Okay. So that's all we have in this section. We just wanted to introduce 3D space to you, get you to understand things like regions, what objects would look like. Everything you thought was a line isn't really a line, it's a plane. Sorry to break it to you. What you thought was a circle isn't a circle, it's actually a cylinder. This, by the way, kind of tells you why vectors is actually going to be important, because now you're going to realize that there are a lot of things that in the 2D conception of the world, a lot of equations made sense for you in the way you wrote them down, but now they don't make sense anymore. If you wanted to talk about a circle, you can no longer express yourself as x squared plus y squared equals 1, unless you add a whole bunch of other restrictions to it. So the vectors is going to provide another way to talk about these objects. So that's 3D space. This is the 3D rectangular coordinate system. This is the XY plane, the YZ plane, the XZ plane. Space is now split into 8 octants as opposed to 4 quadrants, numbered like so. But the main one for you to know is the first octant, which is when the X, the Y, and the Z are all giving you positive coordinates. Objects, you should realize that a lot of things, most of the things that to you was a curve in 2D is now actually more of a cylinder in 3D. They would have to extend in all directions as long as you're maintaining the coordinates that are mentioned in the equation. And And distance is measured very similarly. You just kind of add a third component to your distance formula. Spheres are also measured very similarly. Again, you add a third component to the formula of a sphere. Spheres are very important. And just regions. It turns out in the same way that now in Calc 2 and Calc 1, where we're integrating along intervals, pretty soon we're going to want to integrate over objects, integrate on surfaces. Like forget about subintervals. We're going to take an object and slice it up and erect boxes on that and do like a 3D Riemann sum, right? It's coming. Not in this class, in the next class, but it's coming very soon. Some of you are going to be taking that class in the fall, so it's going to happen very soon. So being able to sketch the region in the first place is going to be very important, because then you can visualize how you're going to set up an integral, how you're going to set up a problem, how you're going to do some sort of calculation. Knowing what the picture looks like can be very helpful. So you do want to know how you're going to actually sketch things in multiple dimensions. So that is important. So that is introduction to the 3D space. Now what we're going to do, and we're not going to finish, but we should get through a decent chunk of it. I'm going to talk to you about the main way that we are going to move around in 3D space. And actually, this is going to be the main way that we're going to move around in higher dimensional space as well. I'm going to talk about vectors, right? And it turns out, once you start to imagine the world in terms of vectors as how you get locations and trace out curves and surfaces, it turns out you'll never need a retranslation forever now, right? Before, curves that we saw in 2D, now there's something else in 3D. What I thought was a circle is really a cylinder. What I thought was a line is really a plane. It turns out once we learn about the vector way to look at things, then you'll never actually need a translation. If someone goes into 4D, then exactly the kind of notation we use, the vector notation from 3D, is going to fit very nicely with that new world. So all you do when you go up bump up a dimension, you just add a component to your vector, and everything else stays pretty much the same, right? And so that's really nice. So we do want to learn about vectors, okay? So like I said, when it comes to describing objects and movement in n space, vectors are indispensable. They give you a much more efficient way to write things down that don't change depending on the dimensions that you're in. We can use vectors to even go back to 2D and rewrite things in 2D. So a vector is just a quantity having both magnitude and direction. And geometrically, we represent this by an arrow or directed line segment. So I would have like, just write an arrow. And that represents a vector to me. This point here is called the initial point of the vector. This is where it starts. And this point here is called the terminal point of the vector. That's where it's end. And the length of the vector here tells you the magnitude. And that's kind of it. I can just describe some sort of magnitude of a quantity, and then I can describe the direction in which that quantity is moving with the direction of the arrowhead, right? So that's really all the vector is. There are quantities that only have magnitude, and we call these guys scalars. And potentially they have a sign magnitude, but we call scalars. So there's a difference between a vector and a scalar, right? And a scalar is just a quantity that only has magnitude. So we'll get to that. We'll talk more about that later on, right? So I told you about the initial point and the final point, right? Now we can name vectors. So I can have a vector over here. I can have a vector over here, and I can name that vector A, and I name it with A with an arrow. So there are two ways that we denote vectors. Either we denote it by boldface, but that only really works if someone's typing. You don't want to take that time writing out. If someone's writing down something with a pen or pencil, we'd just put a little arrow on top of the letter to represent the fact that I'm thinking of a vector. So if I write A versus A with an arrow, those are not the same thing. That's what I want you to realize. Writing the arrow over it, this guy is a vector. This guy is a scalar. Now there's a difference when you write the arrow. Also, if I call the starting point A, and the ending point B, so if A is the initial point and B is the final point, a standard way to name a vector is to say A, B, and then write an arrow in that direction. So this is saying it's the vector going from A to B, right? All right. So that is a vector. It's a quantity that has magnitude and direction. We can name them. If you're naming a vector, write an arrow over it. And you're going to want to distinguish between vectors and scalars and vectors and other coordinates. We'll talk about that later. Now, equality and position vectors. Here, I should probably talk about equality of vectors specifically. But yeah, so here, a vector is uniquely defined by its magnitude and direction, meaning in general, a vector can be moved around in position and we don't care. So if I have a vector over here where its length is 1 and the angle it makes in space is 45 degrees, and I have another vector over here, that doesn't look like the same thing, and I have another vector over here whose length is 1 and makes an angle of 45 degrees with the horizontal, as far as I'm concerned, these are the same vector. Vectors can be moved around in space without consequence. As long as you have a certain magnitude and a certain direction, you are the same vector. And there are many ways in which your notation for that vector is going to be exactly the same, despite the fact that it is it can be in various positions. There's one thing that is an exception to this rule, and it's something called a position vector. So when we talk about position vectors specifically, we always think of the initial point as being the origin, right? So I can have the same vector, again, length 1, with an angle of 45 degrees, and I can call this guy a position vector. Since initial point is the origin. So in general, vectors, you can move them all around. But if someone specifically uses the phrase position vector, they're definitely thinking of the vector as being emanating from the origin, right? So that's very important. A position vector versus a vector. We are going to define curves and surfaces and all sorts of things in terms of position vectors. When we start to get new equations for circles and all that stuff, we're normally going to cater those definitions towards position vectors, because those are the only ones where everyone agrees and knows where they're starting from, where the head is, where the tail is. So position vector is very important, but in general, vectors can be moved all over the place, and we think of them as no different. Vector is described by its magnitude and direction only. All right. So now, and whatever I just said, I just typed it up here. Okay. Now, here's the nice thing about position vector. And I mentioned that here. Is that position vectors can help us define locations. So if we have a position vector, they can be denoted very similar to how coordinates are denoted. So if I'm over here, and let's say this is just X and Y, and I have a position vector that hits a point here, let's call it A1, A2, then the vector here is going to be A1, A2. I can use that notation, and this is the vector, whereas this is a coordinate. So in the vector a1 comma a2, the a tells us how we move, how far left, right. Where right is the positive direction, left is the negative direction. And this is about how far up, down, right? So you can actually think of a vector, you can write it almost like a coordinate, but with angled brackets. Very important that you put the angled brackets to represent a vector. And that's what we are doing here. Did I spend dimensional? Okay. So that's what we have here. So this is like a mathematical notation for a vector. To a two-dimensional position vector whose terminal point is a1 comma a2 is angled brackets a1 comma a2. Three-dimensional angled brackets a1 a2 a3, and so on and so forth. And this actually goes further in n dimensions. Eventually we will get there. Well, not we, but you at some point in the future, probably, if you're a math person. And the components are referred to as the ith component. So I can say something like the first component, second component, third component, fourth component, etc. But in R3 and R2, we normally refer to them as the x, y, and z component, right? So for example, the vector 1, comma 2, comma 3, 1 is called the x component, 2 is called the y component, and 3 is called the z component, right? And we can actually sketch the vector. So yes, Jason. So now, going back to 3D. So we're in 3D now. So at first, we sketched this guy in the last section. So again, I would first find 1 on the x, 2 on the y. Those guys come together like so. Find a point here, and then you raise up to a level that's 3 on the z. Here, you're going to have the coordinate 1, comma 2, comma 3. If we have the origin, a position vector that's based at the origin and extends to hit that point, that is the vector 1, comma 2, comma 3. Okay, so that's how you can actually sketch the vector. And sketching vectors in 3D is a little bit more, it's harder to visualize sometimes, and sometimes sketching in 3D is hard to visualize in general, but that's how you would sketch a vector if you ever had to sketch a vector. You first just use rectangular coordinates, find the coordinate, as I showed you last time, and then a position vector is just going from the origin to hit that coordinate. And I can call that vector that. But again, if I move that same vector out here, same magnitude, same direction, I can still think of it as 1, comma 2, comma 3, non-position vector. It still says move 1 unit in x direction, 2 units in y direction, and 3 units in the z direction. And I can start that from any point technically, but if I start from the origin, it's called a position vector, and it's more easy to see. Now, how do I find a vector with an initial point and a final point that I know I want to be the initial point and final point? It turns out you can do them by subtracting the final point minus the initial point. So component-wise, x component minus x component of the final minus x component of the initial, y component of the final minus y component of the initial, z component of the final minus z component of the initial. So this is how I would create a vector a comma b. So for example, if I have a vector that it starts out at 4 comma minus 2 comma 0, and there's another coordinate 1 comma 3 comma 5, and I care about finding the vector. I was thinking of drawing that in the thing. I'm thinking about finding the vector that starts here. It starts here at 4 minus 2 comma 0 and ends at 1 comma 3 comma 5. Then if I call this vector A, then your A is going to be equal to 1 minus 4, 3 minus a minus 2, and 5 minus 0. So this is going to be the vector minus 3, comma 5, comma 5. So if you wanted to start from scratch, you would move 3 units in the negative x direction, 5 units in the positive y direction, 5 units in the positive z direction. You would create this vector. And that is how I can write it down mathematically. It's minus 3, comma 5, comma 5. Now, on the one hand, I don't know. Is everyone with me so far? Am I leaving anybody? I'm talking kind of quickly. I don't know. So now let's talk about some properties of vectors. Right, I feel like a lot of you would be familiar with vectors already, but just stop me if I'm going too fast. All right, so properties of vectors. Magnitude, or the length of a vector with components A1, A2, A3 is given by this. And again, it's just like using the distance formula. Right?
It's the Pythagorean theorem.
It's exactly the Pythagorean theorem, yeah. So imagine that I had this vector, again, and here in the example above, 4 minus 2 comma 0, 4 minus 2 comma 0, and I can think of this as x1, y1, z1, and I had another point up here, which was 1, 3, 5, 1, 3, 5. And so this was the vector. And I wanted to find the length. It's just the distance between these 2 points. And so if this here is x2, y2, z2, then that means my distance is going to be, well, the square root. Just got myself in trouble with all these colors, but I gotta commit. Move this chat box out of the way. I would actually subtract the x2, the y2, the z2 from the x1, the y1, the z1, but these guys are actually the components of the vector that I had before. And so that is the magnitude of the vector. Now the magnitude of a vector, I call it this, or some people like to emphasize with a double magnitude like that. It's really up to you, whichever one you choose. There's no real reason to use a double absolute value, because once you actually write a vector inside of here, everyone reading is going to know that you mean the magnitude of a vector as opposed to the absolute value of some function. The arrow is what's going to indicate that you're actually talking about the magnitude of a vector. So ultimately, that leads us to the following. The magnitude of A above is actually going to end up being the radical of, we found the vector above, it was minus 3, 5, 5. So it's going to just be the first component squared plus the second component squared plus the third component squared. So that gives you radical, I think it looks like 59. Ah, so close. All right.
That's what I got.
Awesome, right? And that's how you find the magnitude of a vector, so that's the length. You should know this formula. The magnitude of vector is just the square root of the sum of the squares of the components. You should just, that's actually a formula you should know. Everything that I put in a box you should know. Okay. Now let's talk about operations with vectors. There are 2 main vector operations, vector addition and vector scalar multiplication. They are defined as follows. They are actually defined very naturally. right? So if I want to add two vectors, you actually add the corresponding components. You add the x components together, add the y components together, add the z components together. If I want to find a scalar multiple, so remember a scalar is something that only has magnitude. Normally this is just a real number for us, right? So if I have a constant times a vector, like a c times the vector a, it just means I multiply each component by c. There are some important things that you want to note here, and I probably should have put that in boxes, but important things you want to note here. If c is greater than 0, meaning a positive number, then CA has the same direction as A, the vector A. C is less than 0, then CA has the opposite direction as A. So remember, that's the same idea where when we take negatives to mean a change in direction. If C equals 0, then CA is called the 0 vector, right? So that's a vector where there's zeros in all the components, at least in our conception of the world. That's what a 0 vector looks like. And that's a whole other guy. It has no definable direction. It kind of has all directions and no directions at the same time. We'll start to talk about that guy.
Therefore, the vector is nothing.
It's not nothing, technically. It's something. It's just not something that we can understand in the usual way that we understand vectors.
The reason why I said nothing is all because it's 0. The vector is 0.
The vector is not 0. The vector would be a coordinate where there's zeros in each coordinate. It's not the same as saying the number 0. So it's actually pretty different. There's a difference between 0 and saying a vector with zeros in all the components. So there's a 0 vector. It's a whole other base. We'll talk more about it moving forward. The vector a plus b, when I add a vector to another vector, sometimes you call this a resultant vector. That's what I have here. More of a physics term. We probably, I'm not sure if you'll ever see that in like your math homework or any math book, but in physics a lot you'll hear it called a resultant vector. That's what it means. Okay, now let's talk about geometrically what it means. So computationally, here's how you add two vectors. You add their corresponding components. Pretty easy peasy. Geometrically, what does it mean to add two vectors? Well, if I have a vector a plus b, this is a vector that has the initial point of A and the final point of B. It kind of means that I take one vector, start out with the vector A, and then to the head of vector A, I attach the tail of vector B, and then follow the B to its terminal point. So if I have a vector A like this, and I have a vector B like this, then if I go to A, and I attach B, then that new vector that's created, that has the initial point of the A and the final point of the B, that is the vector A plus B. And so that is how I can find a resultant vector. Right? Now, negating a vector flips its direction, right? So if I have something like here is A, then if I were to look for minus A, it's just exactly the opposite, okay? All right. Also, this leads to the concept of subtracting vectors as well. What does it mean to take A minus B? Well, we think of A minus B as A plus the negative of B, which again, computationally, it's pretty obvious how to do that. You subtract corresponding components. Geometrically, what it means is you first find minus B and then you add that to A. So again, let's say my A was here and my B was here. Then my minus B is the other guy going here. And so A minus B is the same as A plus the negative of B. And so what that is going to look like is I'm going to start with A, and then I'm going to add to it the negative of B. And so that would be the vector going from here to there. So this is the vector A minus B. Make sure you're paying attention to this because students often mix this up. Last semester, they mixed it up a lot. Some of the students felt like, oh, I'm awesome with vectors. And so when I'm explaining these basic things to them, they kind of half zone out and then they get in trouble down the road. So I'm talking about very simple things and you guys seem to be following, but make sure you're paying attention. Just to make sure that you know the difference between the two. Here is A. And if I have a B, it would go in this direction. If I had a negative B, it would go in this direction. So A plus B has a completely different direction from B plus A. And you need to understand that those two will have a completely different direction. Right? Now A plus B, in fact, it forms the other edge of a parallelogram. If you imagine that A is one part of a parallelogram and B is another part, you can kind of imagine that there was a parallelogram being formed here with B on the other side and A on the other side, and the sum is just the diagonal of that parallelogram. This is not true for the difference. The difference is actually pointing outside the parallelogram, going the other way. So it's very important that you understand the difference between the two. The difference, in fact, would actually be the diagonal going the opposite way, like here. So that red would be the A minus B. So there are two very different directions and you don't want to mix them up. Later on, I'm going to talk about some stuff and I'm going to derive formulas using A minus B. And a lot of times students mix it up with A plus B. Don't be that guy. Okay, two vectors are parallel if they're scalar multiples of each other. This is one reason why a zero vector is such a complicated thing. It's actually parallel to every other vector. So by this definition, the zero vector is parallel to every vector in existence, including itself. Later on, we're going to learn that the zero vector is also perpendicular to every vector, including itself. So it's kind of a vector that's parallel to everything and perpendicular to everything. And that's why the direction is undefined. It's a thing that we can move around and manipulate. But
it's 2 minutes past 7:40. So, like, you know, just to let you know, it's already 2 minutes past 7:40.
Yes, I'm aware. Thank you. So two vectors are parallel if they're scalar multiples of each other. So it means if I take a vector and I multiply it by a constant, I get something that's parallel. So if I have, say, A is this vector, then if I were to take 2A, it's going to be parallel in the same direction, but it ends up scaling, right? So it's twice as long. So if this guy here had length L, this guy here is going to have length 2L. And of course, if I scale by a negative number, say minus 2A, same sort of idea, except again, it flips the direction. Here, length still 2L, but opposite direction. Okay, so those are that's something you need to know. Also, vectors obey these properties. So you should know that. A lot of people know this intuitively, but there are a lot of things about vectors that are actually not intuitive. One of those things is you might notice that I totally skipped over multiplication. You told us about how to add two vectors and how to multiply a vector by a number, but why didn't you tell me about how to multiply vectors? Well, it turns out that vector multiplication in the strictest sense does not exist. You can't really multiply or divide two vectors. We're going to talk about things called products later on, namely the dot product and the cross product. And I don't want you to think of these guys as multiplication. They're just a way to create a scalar and a vector quantity respectively that has a useful relationship to the vectors involved. All right. That being said, we're going to end right here. I'd like you guys to do these examples to start off next time. You guys should be able to do all this based on what I gave you before. It's not
Professor,
crazy. Yes.
will any of the vectors be on Monday's quiz, or it's
Yes.
gonna be on Monday's quiz? It's
Yes.
gonna appear as the bonus. It's gonna be a part of the original questions too as well.
A part of the original question as well, because I got through a lot of the vector section already.
Okay.
Bonus might be these guys stuff down here, IJK notation. Unit vectors might be the bonus. And I'll leave these here in the PDF for you guys. But once I get through these few calculations, which you guys should be able to do, and then I'm going to talk about IJK notation and the fact that you should not mix notations, something that happens all the time as well. And I'm going to talk about unit vectors, which are uber important. That's going to wrap up our vector section. So try these for next time. And we are going to end right there.
It's basically the vectors is going to be like more conceptual, or is it going to be more like computational?
Well, it's a multiple choice, so I mean, it's always going to have some concepts in there. Anyway, that's it for today. Exciting lesson, at least I thought so. It's a brave new world. We're now looking at stuff in 3D, and it's going to only get more interesting from here on out. I will see you guys in the next one. Quiz on Monday on everything that was since the first test right up to vectors. The bonus is going to start from unit vectors and IJK notation. Maybe I might ask you some stuff about dot product and cross product as well. All right, take care everyone, be safe, and that's it for today. I will see you guys in the next one. Ciao.